Hello everyone, it is November 26th, 2024, and this is the bi-weekly libhal meeting. For our agenda today, we have quite a few things to go over. One of them is going to be the STM32 Web Flasher web tool. It's really exciting and it's really cool. I can't wait to talk about it. Next up, we have a little discussion about the future of new interfaces, which will be that they'll have their own repos, and I'll go over what that means. And also, I'd like to talk about libhal 5.0. There are a number of things to talk about in 5.0, quite a few changes. They're minor changes, but there are a lot of them. I don't think they'll change a lot when it comes to how the basics are still there, but there are a lot of things that are being optimized and tuned for use cases that have come up. And we're going to go over items A to G, and then later on we'll go over H to however many we can fit in that week. And there may even be potentially even more than these. So these will probably get stacked and combined together while we go over more and more of the changes in libhal 5.0. So first off, let's take a look at the web flasher. So here's the web flash website. We still need to do some fixes on the CSS, but one of the cool things about this is that we're developing a board called the HAL board. It's cool because it's going to have a debugger. It has a debugger on it. And the game plan is to also introduce a logic analyzer as well. Something simple like what you can create with a pretty much any old microcontroller, but I think we're going to use like a Raspberry Pi 2040 because there's already a logic analyzer firmware out there. But all you need to do, this device allows you to connect up both. It's all connected via a hub. Yeah, plug this in, go to SimSys down debugger, press connect, select the appropriate debugger, click this, and now it's on and flashing. And it's complete. Now I have a functioning debugger on one of my devices. So this is one of the cool things that we put together. Our hope is in the future, as we provide more hardware for people to use to develop things, that we can have a nice and easy website that you go to that just flashes everything. For example, in the future, we'll probably also have a RP2040 flasher, which is kind of weird because they use it uses the file system. It comes up as a flash device in order to flash, but we're going to come up with some way to basically flash both of these so that you can just come to this website, click a button, and then everything gets done for you, and you're ready to start sampling and doing stuff. But yeah, that's the libhal STM32 web flasher, which we're going to make sure to tune to specific applications in the future. So yeah, that's the web flasher. Next up, we have the future of new interfaces and new repos. So what does this mean? As time goes on, I want to, when I think about things like libhal or when I think about USB, one of the things that I'm concerned with is, let's say we discover that there's something very wrong with USB. And because there's something wrong with USB, we have to update it. And that causes a breaking change for libhal, which might be pretty, have a lot of ripple effects. It'd be good to potentially mature a package before we bring it into mainline libhal. I know Embedded Rust did this. They did this for CAN. Rather than just bringing it in automatically, they had it be in its own repo until it reached 1.0, and then they merged it in with the Embedded Rust. And I think that's a good idea. So this basically just protects against libhal having constant version breaks. And the way we would go about doing this would be that we would do this with like libhal USB as practice to get an idea about what it's like to build up a package and build it, and then eventually merge it into libhal. The idea here would be that the version numbers for this package would go up as the APIs break and as the APIs change. So we might, for libhal USB, have multiple options for how we do USB to figure out which one performs the best, and then get rid of the ones that we don't need, and then kind of slim it down until we eventually just have like the version that we believe works the best, or the set of components that are necessary to make it work. Maybe we have different versions of a control endpoint. I'm not sure. Not too important to be too concerned with, at least at this moment, but we'll build them out. We'll see what works well. And then once we get to whatever version number at the end, we'll take that and add it into libhal proper. So I could imagine maybe the final version of libhal USB being 10.4.1, and we take candidate 10.4.1, we make that the interface that's brought into libhal. And let's say libhal is version 5.6.7, that would bump it to 5.7.0. So it would just up it by a minor number because we added a new interface. So yeah, that's kind of the idea. And I think that would keep things rather stable on libhal going forward. And this is mostly for adding in new things, just so we don't have to go back and make big changes. So that's that. Now for 5.0 things. So A was on the first thing to talk about is how with 5.0, and this is actually going to be available in 4.0 as well, so it's not that big a deal. But I also wanted to introduce it that we now have shortened names for the different integers. So this adopts the naming scheme that's used in Zig and Rust, which is calling U8 for a standard uint 8, U16 for a standard uint 16, and so on and so forth. To write these out would be hal : then whatever these numbers are. This makes everything a lot shorter, a lot easier to write. And yeah, I think that's just the better way of going about it. Next up, and I'll be using those, as we go through these slides, I'll be using those things that we learn in each slide for the next slide. So for example, we'll be using a U32 for the clock and baud rates. So before we were using floating points to represent hertz, and that's fine-ish. The problem is that unless we have something that's going to be above 4 gigahertz in speed, which I think in general for a lot of the devices that we're going to be dealing with, that's not going to be the case. And if we do hit a situation where that's required, that might be a situation in which a new interface is warranted versus using the normal interface. But I think in most cases, the only things that it'll have, I think in most cases that's not going to be something we have to worry about. But when it comes to the frequencies here, basically floating point gives us a lot of flexibility, but we don't really need that much flexibility. It's unlikely that we'll ever set a clock rate to below 1 hertz, so having something fractional below 1 isn't useful. Having a fraction on top of a rather large frequency also isn't helpful too. Like for example, if you consider 100 kilohertz, and then if you set you wanted it to be half a hertz on top of that, that's so little that adds so little to the overall frequency that it's pretty much a rounding error. Not exactly, but for the most part. So to me, I see this and I think to myself, the fractional part, the decimal part of the frequency is not useful. And we don't need small frequencies that are sub 2.25 or something like that. That's usually not what people ever develop or design around. So floating point doesn't give us any flexibility that we actually need. And because of that, there's no reason to pay the cost of it when we're not really using it for anything useful. So yeah, all the clock rates and baud rates will be switched over to U32. I've kind of flip-flopped on this, but it's less of a flip-flop and it's more of that I'm becoming more focused and on what things should have floats and what things should not have floats. And I think that percentages and proportions should not use floats. Currently throughout our code base, we use the float 0 to 1.0 or -1 to 1.0. I don't believe that, after thinking about it, I realized that if we use the full scale of N16, that's still a pretty good amount of precision. Not only that, but it also allows the code, it doesn't add another dependency on floats, and also, where it's not necessary. And also, we don't have to do any clamping anymore. Once you do full scale and you use the entire range from negative to positive, clamping is no longer required because it just isn't applicable. The entire space is available to you. So it gets rid of a clamp, gets rid of a conditional branch, and replaces it with just a full number. So main rationale is that floats have a size and performance cost. So size, if you don't have an FPU, so you'll have to emulate floating point arithmetic in software, which costs the actual function calls in software, and also takes longer to operate with, whereas proportional numbers can be easily used to scale a number for the PWM or for the motor. Rationale 2 is that I was thinking about the precision that you can get from just a U16, because I considered maybe using a U32. uint16 is useful on 32-bit systems because you can multiply two U16 numbers together, and that operation can fit within a 32-bit number, meaning that your multiplications are fast. Before, just a little reminder, before when we were doing a lot of work with floating point, the operation we were trying to use, not floating point, with fixed point, we were trying to use fixed point everywhere for all types of proportions, for all possible things, and that got really complicated and really messy. But if we just use it just for the proportional side and keep everything within 16 bits of resolution, you can actually have your operations be very fast. So this beats out floating point in terms of performance by a long shot, by keeping everything within 32-bit resolutions. Again, the mistake we made last time when we did floating point was that we had two 32-bit numbers that we multiplied together to get a 64-bit number, and division and multiplication into 32 to 64 on a 32-bit system is expensive. This is cheap. So with 16 bits resolution, you get 0.00153% of resolution per digit. So if you needed to change your PWM duty cycle, you could kind of round this up to maybe like, I would say 3 per like 2 digits. And now you have like almost here like a 1,000th of a percentage. It's a little bit more than that. It's like a 1,000th and a half of percentage. But I think that's pretty good for most use cases. I think that much resolution for the PWM proportional number can get you pretty far. Same thing with motor. I don't even know if you've at that point exceeded the precision that most motors could even deliver power to an actuator. So I think that's pretty good. It fits our use case, and it's easy and fast for our devices to do operations on. Next up, I want to reaffirm floats as our sensors direction. This just means that I want to continue to use floating point numbers for voltage sensor, current sensor, accelerometer, gyroscope, and things like that. And the reason why is that I looked at Zephyr and I think a couple of other hardware abstraction layers out there. And from what I could gather, I think they do their own little form of fixed point, and they also have like what the minimum fixed point value would be for voltage. Let's say it's like, I think, microvolts. Cool, that's a way to do it. The problem that I have with that is that this now means that your voltage, like the minimum that you can have in terms of voltage that you can sense is microvolts. And I think it's definitely possible to be able to sense less than that. You might have like a very sensitive apparatus that's able to sense something like that. Or you could also have something in the scale of kilovolts. I think that rather than trying to come up with a fixed point representation for the thing that I think people will use the least, just let the flexibility of float allow itself to express whatever. Current sensor will return back a value in amperes. And how many amperes, like what the scale is, depends on the floating point number and what the application is and what the sensor does. So to me, I think that it makes sense for floating point to stay here. I guess potentially, if I was to flip-flop on this again, it might be that there might be like a low voltage sensor and a high voltage sensor. I don't know if there is a use case for specifically those, but I can tell you that when I spoke to a couple of my developer and firmware friends who work with sensors, specifically accelerometers and like IMUs for either data acquisition or for consumer electronics, they all said that they work with floats and that they don't have really a utility of not working with floats. And it's really useful to just have your accelerometer give back G's. And one of the things that they expressed to me is that it really depends on the accelerometer and what it does for you. For example, some accelerometers will give you back the information in a really simple and easy to acquire way. Some of them will require have temperature compensation. So you read out the accelerometer values, and then you also at the same time read out a temperature sense value right after the accelerometer data or IMU data. Then the vendor may give you like some equations to use in order to couple the temperature sense data into the accelerometer data and gyroscope data, compensate for it, and then use those numbers in order to actually come up with what the G's would be based on what you set the maximum scale to be. So like there's a lot of complicated bits there that like you, if we could have figured out a way to like return back what a like milli G is or a micro G is to kind of to set the scale, but I think it's just kind of important to keep the values in floating point. Basically, I am concerned that there might be a certain type of sensor where whatever scale that we set for the minimum just doesn't fit that thing very well. And we end up making a bad choice there. So I think floating point still works out pretty well. And everyone else I've worked with says just stick with floating point. It makes the math and doing work with the numbers so much easier than having to deal with the fixed point stuff. So yeah, floating point staying there. All right. So, tagged callback functions. The idea here is before, when we had like, let's say we looked at a timer class, we'd have a function called schedule, and it would just take void and void because it didn't take any parameters, it didn't return anything. You just give a function that you want to do something with. Now that's all good and fine. That works just fine in libhal in general. But one of the things I've been thinking about is a tool that I am working on a proposal for, which is called the advanced exception tools. These advanced exception tools allows your code to, the goal is to allow you to scan your binary, find all of the functions that throw exceptions, figure out the call graph, and then determine and simulate all exceptions being thrown, and then figure out which ones meet at termination spots, either no except functions or main. Now, the cool thing about this is that you can get full analysis on how every single one of your exceptions would propagate through your code. And we hope to add a whole bunch of really cool features there. But there is one thing that makes, there are some weaknesses to this analysis. And it's kind of just a weakness in how abstractions work in general, or polymorphism works. So in the case of virtual functions, I'll go over that in a little bit. Because we don't, if you take a class by its parent to the point where you erased where the concrete class's signature is, we have no way to know that you had made a call to one I2C versus another one, or to one type of pin. There could be one pin that is built into the actual device, like an output pin. But there's another output pin that's connected up to an IO expander, and the IO expander talks over I2C. It can throw an exception. So what we're gonna do in the advanced exception tool is fuse all of the calls that have the same signature into one, and say that if any one of these can throw an exception, all of them called from that point can throw that same exception. Same thing with callbacks. So the issue that I had was that before, when we had schedule just take void and void, it meant that every single callback that existed within the entire code base that just returned back void and took no arguments would basically, any function that ever called any one of those would propagate those exceptions. So you get exceptions being thrown all over the place throughout your code base, and it'd be really difficult to figure out which ones actually are false positives from callbacks and which ones aren't. So this is really to disambiguate which callbacks go to which things, because I know for a fact that a lot of different callbacks will or will not use code that could be throwing. There's a lot of use cases where you're going to schedule something, all you're going to do is change a bit somewhere. That will ensure that there won't be any type of exceptions in schedule type things, but there might be a lot more in other types of callbacks. So this is really just a way to future-proof the code so that a future tool can work better for it. That's the quick and simple of it. Here's a bit of a diagram to kind of represent what I was talking about before. Let's say we had some scheduled callback, a loop handler, and a frequency switcher that all basically fit this signature of function that returns back void and takes no arguments. Schedule callback doesn't throw anything, but loop handler throws how timed out and no such device, and frequency switcher returns back operation not supported. Since this function call could work with any one of these, in the code it doesn't know which one of it's going to be. So it has to assume the worst case scenario, which is that it's all of them. So it just concatenates all of the entire set of functions the exceptions that can be thrown, and assumes that any function call to a function pointer of this signature can throw all of these. And this is a way to separate that. If you do this, now, if this is part of just schedule, this is part of some other loop type handler thing, and this is part of some other type of frequency control thing, then this only fits for whatever this single parameter would be. That would switch that to something like schedule tag. And now it'll only be what schedule tag has. And then the analysis tool would basically say, this function, these set of functions, these function pointer calls never throw anything, reducing the overall surface area of things you have to check. All right, so we've gone over a lot of things. I think we're getting towards the end. One of the bigger items here is adding a onWait API to IOWaiter. So the idea is to inject a function call before waiting on IO. This function allows application code to inject functionality into an IOWaiter before performing a wait. The idea is you could basically just subvert and control what an IOWaiter does in order to benefit you. And then I'll just go over the API real quick so it's understandable. So we take an optional HAL callback for a function that returns nothing but takes a onWait tag. It's just a single parameter. You don't actually even give it a name. You just need it to be there so that we can disambiguate it. Now, if you put null opt here, the way that this is supposed to work is that it disables the callback. If you put an actual function here, then it'll pass through the callback. Rather simple to utilize. I did not write that in here, so I need to make sure I do that in the actual documentation. But that's pretty much what happens. The way that I expect people to use this is, let's say we have a timer and we have an IOWaiter, and we have to do some work. And what we want to do is we want to say, if we're stuck in IO for a very long period of time, like we're just, just stuck there looping, I want some way to kick the system out of that. And last time we had this meeting, I talked about what's called asynchronous or remote exception unwinding for threads and all of that. I like the idea. I still like it. It's just the problem is that it just requires a lot of memory. But here's another option. We can put in hooks, and the hook that we need is the IOWaiter. So since all of our things that do IO and pretty much have the ability to stop themselves, or I'm actually probably going to posit that almost every device that does some sort of blocking IO have an IOWaiter, just so that there is a way for the application to inject some actions in between. The idea here is we take this timer, we schedule in some time, about 250 milliseconds, and if that happens, we want to execute this function. So it takes the timer as a reference, it takes the IOWaiter as a reference, and then takes a schedule tag. This is just because this particular, this schedule takes a schedule tag, IOWaiter take an onWait tag. And all we do is we set up IOWaiter to onWait, throw an exception called timed out. So here's the whole idea underneath. This is going to do some work. It's going to call some class or some object like SPI or I2C or UART. UART usually doesn't really need this, but I2C or SPI. When those particular APIs are doing their thing, if at any point you call the wait function and the onWait function has been set to this, what'll happen is that it'll call this function prior to it waiting. That function will throw an exception, which will burrow its way all the way through your code until it gets out of this. And this is how you can figure out if you have hit a deadline violation. And actually, what I probably would have done too is add a try catch. Not a lot of space for this, but I would have added a try catch here to catch a timed out exception, and I would know that. So this is a way to schedule a way to break the code out of a loop and say, hey, you timed out, we need to do something different to change strategy. And another inspiration for this is that you can also use this in order to stage operations. So kind of think of this as if we were reading something off of an accelerometer or some other device. And in this case, you would have a couple of devices device drivers or peripheral drivers that are all using the same I/O waiter, which is important. So you pass those on to a couple of accelerometers, and what you do is you set up the on wait to do stage 1, and then you call that read function or whatever. What happens is it begins reading. It starts the transaction with the other what's what I'm looking for. It starts the transfer, and then it begins to do its operation. So it'll call wait, which will then call this handler, and then in this case, it just kind of prints out stage 1. It sets the next on wait handler to stage 2, and then does the operation. And calling .wait is a equivalent of doing that operation. Then when that thing does its operation, sets everything up, and then tries to ask to wait, we'll then call stage 2, which then stops the whole sequence by setting it to null opt and then calling that operation, calling whatever final operation needs to call. The whole idea here is that you can nest additional function calls to trigger more actions to happen, all without needing any context switches or anything complicated like coroutines. We could implement a coroutine like system that does this for you outside of all of this, so you can like not have to like do all of like this kind of confusing stuff. I'm also writing like a function that does this, wraps all this stuff for you. But this is what this thing gives us. This is really useful for Gene's project actually, where he's building a glove, accelerometer glove, where there are like 5 different SPI buses, and we want to DMA all of them all at the same time to grab all the accelerometer data very quickly. But this will require us to have a couple of threads for each one of those if we wanted to use the normal I/O wait paradigm, which is keep everything blocking for the thumb, execute the transfer, then sleep that thread, go to the next one, transfer that, do the transfer, sleep on the wait, next one, sleep on the wait, do it all until they're all finished, and then they'll all wake back up when they need to, give the data to whatever needs to be given it to. Another thread will aggregate it and will shoot it off over serial. We could use FreeRTOS for all of that. You can also stage them out like this and have them all kind of happen all at once in a single thread. Again, if this particular application doesn't really require doesn't need anything. It doesn't need to be that real time. Or I'm sorry, I was full back. It only has one real time requirement, which is gathering that data and shipping it over serial. And because of that, it could still be kept in a single thread. So I wanted to make sure that I/O waiter had that kind of capability because it makes it more flexible into the future. I think this is going to be the last one. Let me check. Yes, it is. So I am also removing frequency control from I2C and CAN. So it might be a bit of a shocker. But I realized that frequency control on CAN and I2C just didn't make any sense. But yeah, what does this mean? You'll no longer be able to rate control the clock rate. So right before we had a configure and you'd be able to control the clock rate there. Now that will be gone. So CAN, which had only one configuration option, which was clock rate or baud rate, that's now removed. So there's actually no more configure for CAN anymore in 5.0. For I2C, there will be a function and actually for CAN as well, there'll be a function that allows you to get the current frequency. And that's how we're kind of doing things. We're going to invert this. So the clock rate is either set at the constructor or as an out of interface function. So the concrete class would have the function for you. Device drivers can no longer change I2C or CAN frequency. Instead, they must throw a how operation not supported exception if the frequency is above their maximum the chip can handle. So let's say you have an accelerometer that can only talk at 400 kilohertz, can't talk at 1 megahertz. And you pass an I2C to it. What that driver should do is check and validate that the clock rate of the I2C is within a reasonable bounds. So for example, if it's 1 megahertz, that's above what you can tolerate, so you should throw that exception. If it's like below that, let's say it's like 100 kilohertz, then you're good to go. And the expectation from the driver is that the frequency will not change on it later on. So one of the ideas I have is that I2C objects, I might frame them a little different. I'm still coming up with the concept of what a device manager will look like for libhal, and I think it'll be different for each type of interface. But the idea would be that you'd have some I2C class that does not implement the I2C interface. But it allows you to control frequency and allows you to do other things. Then you're able to acquire or like borrow or steal or do whatever. You're able to pull out an I2C from it. And what that does is it tells the I2C device manager that, hey, there is a shareable I2C that exists currently. We're going to disable all those other customization functions because now, specifically clock rate, because now we can't allow the clock rate to change. If we allow it to change, that could be a very that could be an issue for any device that expected the frequency to be a specific number. Same thing with CAN. You usually have to have the exact baud rate for the entire network or the devices that you're using. So having CAN provide you the frequency, the clock rate that it's operating at, is useful so that you can see if it's set incorrectly. And yeah, so the rationale for this is that when I was writing the documentation for minimum speed I2C, I realized that there was a glaring flaw in the idea. And it's the fact that there really is no automatic, non-global way to know how to set the I2C to the correct minimum frequency. The reason why is because before you talk the first time on the I2C bus, you needed to already have set the frequency of the I2C to the lowest that the bus can handle. So if you have 3 devices and one of them can talk at 1 megahertz, another one can talk at 400 kilohertz, and another one can talk at 100 kilohertz, you can only talk at 100 kilohertz. You have to talk at the slowest speed. And the reason why minimum speed I2C, which basically sets the clock rate to the lowest it's seen, is problematic is because if you start off talking to the 1 megahertz device, it'll say, hey, look, all right, let me set your frequency to 1 megahertz. And then you try to communicate, you've already messed up because now you communicated faster than the devices could handle, and you could potentially cause them to misinterpret your signals. You would have needed to have done this from the smallest or the lowest common denominator device, and then go up from there. But if you already knew what that device was, then this thing wasn't helpful. You would have just used the number that they told you to use. So I looked at other devices, other abstraction layers out there. Actually, I didn't look at them. I re-remembered how the device tree works for Linux. And I remember the device tree is basically stuck. It's set to a very specific number. You can change your frequencies at runtime, and we will still allow that so long as you don't have a shareable I2C available. But in general, you usually hard code it to a number and you leave it there. And that's gotten me thinking that maybe that's how we should approach I2C and CAN. SPI is going to change a little bit. It will still have the ability to do clock control, but it's going to be even more flexible. You can do clock control with every single transfer API call. We'll talk about that next week. And then, it's not next week, in 2 weeks from now. And then UART also, because there's only one device that should ever use UART. It's basically once you pass it to something, that's something that owns it forever. It'll still have a baud rate control because it basically just allows the driver that you pass it to set the baud rate to what it needs, and that throws an exception if it's not supported, which is what we want. So that is basically the last item here until we go to next week. So check us out the next 2 weeks when we go over the further new things about libhal 5.0.